This is A2Further Pure Mathematics, and we are on Chapter 8, Hyperbolic Functions, and we're looking then at the integration then of some of these. So we'll run through this very quickly. Most of them you'll find in your formula booklets. But sine goes to cosh, cosh goes to sine, sech squared obviously goes to tanh, and then some of the ones from our previous chapter, we'll bring them all together here. Then 1 over the square root of 1 minus x squared gives us arc sine x. If you use that substitution, x equals sine u, you can work it again. It's all in the previous chapter's notes. Arc tan is this one, and then the two new ones that we've just been doing recently then are this one here for r sine and this one for r cosh. So those are the kind of straightforward ones. Then if you change your 1 then for an a, we can get these forms in as well. So it gives us arc sine x over a, 1 over a upon arc tan x over a, r sine x over a, and r cosh x over a. Let's take a wee look then at the first example. This is my second go at recording this video. The first one stopped halfway through for some reason, so I've had already written out annoyingly. We're trying to show that the integral of this gives us this. I've done it backwards here, so I'm differentiating this and ending up with this. So y, I'm letting y equal this bit here, and then the x over a, and I've let t equal x over a. We're going to use differentiation chain rule. So changing that then to t, and we know then that if you differentiate this, you're going to get 1 over 1 plus t squared. Again, it's just back on the previous page. dy by dt then, so 1 over a upon this, differentiating then the t, dt by dx is 1 over a. Dy by dx is then dy by dt times dt by dx, so it's this times by this. That's what I've written down here. That means then kind of back to our first line, d by dx of 1 over a arc tan x over a then is 1 over a squared upon 1 over 1 plus x squared over a squared. So what have I done there? I've changed my t back then to an x over a for that bit. Multiplying through by a squared along the bottom line, that turns to an a squared, that cancels that a squared, so I then just get a squared plus x squared, and we're effectively there. This was a question, if you integrate this, what do you get? So we end up then with that. Alright, on then to our example 2. So we have to find then the integral of 1 over the square root of x squared minus 9, and we're going to use the result then on the previous page. The integral of 1 over the square root of x squared minus a squared dx equals r cosh x over a plus c. If we let a equals 3 in this particular one, this obviously becomes a 9, and it just gives us then r cosh x over 3 plus c. Sometimes, like the previous example, you need to prove it and show where it comes from. Other times then we can just use the standard integrals that we're given. For part B, it's 25 minus 4x squared. Our wee formula only works if that's an x squared rather than a 4x squared, so we need to tidy that up first. So what am I doing here? I'm going to rewrite the square root of 25 minus 4x squared. Take out the 4 here and change my 25 since it's a 5 over 2 squared minus x squared. And if I put a square bracket like that, hopefully you're happy enough. So what is that? That's a 4x squared. We're happy enough that that's come from there. Then the 4 here would cancel in with this 2 squared down here. My next line would then be actually to take this out. So this is the square root of this times the square root of this. So it's the square root of 4, so it's 2 upon then just what I had then in the square bracket. So it's 5 over 2 squared minus x squared. So how does that help us? We are then going to use the integral of 1 over the square root of a squared minus x squared dx, which gives us arc sine x over a plus c. If we let our a equal to 5 over 2, then the integral of 1 over 5 over 2 all squared minus x squared with our half out the front, because we need our half out the front, dx. You see where that comes from? So that was the 2 coming from there, which are rewriting then down there. There's going to be a half arc sine 2x over 5 plus c. You see then where that comes from. Okay, example 3. Evaluate between 2 and 1 over the square root of 1 plus 4x squared. Similarly to the last one, give me your answer to 3 significant figures, so we don't need to worry about ln or e to the x or anything here. We can just work this one out. So similarly, we need to rewrite this. So it's going to be 2 upon a quarter plus x squared. So that means I rewrite this and take the 2 out, but comes out then as a half. So it's a half between the integral 2 over 1 over the square root. That's going to be written as a half squared plus x squared dx. If we let a equals a half in the formula, it's going to be r sine x over a plus c. Again, you can just about see that. Hopefully we're okay. So for a half between the integral 2 over 1 over square root of a half squared plus x squared dx. Half comes out the front here, a half r sine x over a, and remember our a then is a half, so it's x over a half, so it's actually 2x, and that's in between 2 and 1, so it's a half r sine 2 times the 2 is 4, take away r sine 2. Again, with these I'm sure there's some fancy ln answer, but luckily we're told to give it with 3 significant figures. Into your calculator, 2.0947 minus 1.4436 gives us 0.326. Last one then in this video is example 4. So what's it asked? It says the region R is bounded by the curve y equals cos x, that's this one, and the line y equals 3, that's going as shown in the diagram. Find the area of R, giving your answer to 3 significant figures. Hope you can see what I have to do. We're going to have to find the area of this here, and then we're going to find the area of the rectangle, and then take the 2 of them away from each other. So we first of all need to find our values then at a and b, so let's write down that we're doing that. A and B, i.e. when cos x equals 3. So how we're going to solve that, you need to flick back a few videos and get the idea, but cos we know is a half e to the x plus e to the minus x, which is 3. That means obviously e to the x plus e to the minus x is 6. How do we normally do this? We multiply through by e to the x. So we're going to have e to the 2x minus 6 e to the x plus 1 equals 0. Quick quadratic here with this, so we're e to the x then is going to equal minus b, 6 plus or minus the square root of 36, take away 4 all over 2a, which is going to be 2. So our values of e to the x, they're going to be 3 plus or minus 2 root 2, whenever you sit and work it out. That means our values of x or ln 3 plus or minus 2 root 2. Putting this into your calculator just to give us a bit of an idea of the number anyway, if nothing else, minus 1.763 and 1.763. Encouragingly, you can see the symmetry, so those are then those 2 points. So we have that. What do we want to do then? Now, A, B, QP minus the integral between 1.763 and minus 1.763 of cos x dx. So what's this? This is the area of the rectangle. Take away the integral, which will give us the area underneath. So that's our required area. So area of this, that's quite easy. That's 1.763 there, minus 1.763, so it's 2 times that gives me 3.526, you can word for it, and then times by this to get the area of the rectangle. So it's going to be 3 times 2 upon 1.763. Hope you're happy enough with what I've done there. Take away, what do you get if you integrate cos? Of course you get sine. 1.763 minus 1.763. That then gives me 10. I think it's 578 minus 2.829 minus 2.829. Maybe put that part into your calculator. So the area that we are looking for is 4.92